let me spend the last couple minutes and so that's all we need to do to execute the instructions. There's one other thing that any respectable piece of hardware needs to take care of, and that's dealing with exceptions. What do we do if we run across an instruction we can't execute? Its operation involves either like an illegal opcode. I've looked at the opcode field and it isn't one of the ones that's listed as an instruction. Okay, or I'm dividing by 0, or I'm referencing a non-existent memory location. In other words, it's impossible for the machine to coherently, correctly finish the execution of the instruction. Well, choice 1, a very bad idea, is simply to say, oh, I'll just ignore it. I'll just do whatever happens, and, who cares? It's, the programmer will figure it out. Well, it turns out it's very hard to figure out what goes wrong in a program where the hardware is ignoring all the errors. And you sort of say, well, I don't know. I got the wrong answer, but who knows which of the 12, the preceding 10 billion instructions actually was wrong, was incorrect as an instruction or got an illegal memory reference or something like that. Instead, what we choose to do, option 2, is to interrupt the execution of the program. And by interrupt, we stop execution where it is, and we go off and we run some special piece of software that will deal with whatever the exceptional situation is. So these are called an exception, and we have two types of exceptions. We have synchronous exceptions, which come from the execution of the program, divide by 0 in a legal memory reference. And then we have asynchronous exceptions, and those are, I want you to stop execution of the program, not because the program is wrong, because I have something else I want the computer to work on. Like, I got a new network packet, and I want you to go process that right away. And we'll talk more about this sort of time-sharing aspect of saying, stop what you're doing, we want you to go do something else. So those are so-called asynchronous exceptions. They're both very similar in hardware, as you'll see. We don't have to add a lot to the hardware to make this work, and we're adding pretty much the same thing in both cases. So this distinction between synchronous and asynchronous exceptions will become more apparent when we get to operating systems in a couple weeks. The key is we want to be able to stop execution of the program, but then restart it where we left off if we can figure out how to fix the problem. Or we just want to resume execution of whatever program we interrupted to go deal with network packets. Okay. So the implementation is pretty straightforward. We're going to fake a procedure call. It's just a transfer of control to a special procedure in the operating system that deals with the exceptional situation. And we're going to fake a procedure call, and I'm going to show you how that works now. And so we're going to go off and write, instead of using the linkage pointer, we're going to use a special register, which we call the exception pointer, XP, which is R30. We've reserved R30 for all these weeks and said don't use it, we're going to use it for something special. And the something special we're going to use it for is that's where the hardware is going to stick the value, where the address of the interrupted instruction, actually the PC plus 4 of the interrupted instruction. So for example, if you don't have a divide hardware in your machine, this is an illegal opcode, so when it saw a divide instruction, it would say, oh, I can't execute this. I'm going to go off to this illegal operation handler, and I'm going to basically stop. I'm not going to execute this instruction, and instead I'm going to do a forced procedure call, okay, which is just like a forced branch, where I'm going to save PC plus 4 into the XP register, and then force the PC to the address of the special instruction, of the special code that deals with the exception. And so it turns out all we really need to do is to either recognize, decode that something's an illegal operation in our control logic, or take in an external interrupt signal that says, stop what you're doing, I want you to do something else. In such a case, we choose some special addresses, either hex 4 or hex 8 is the new program counter, depending on which exception we're dealing with, asynchronous or synchronous exceptions. And at the same time, we're going to write the PC plus 4 into the register file, except we're going to do it at R30. So here it says XP, but that's actually the 5-bit number, the 5-bit representation of the number 30. So are we all done? Here's our final answer. Regis Philbin would be pleased. Our final answer, okay, for what the beta looks like. It's actually a remarkably simple little diagram, considering that this is, not too different from most of the machines that you'll meet. The other machines are complex because they're pipelined and they're trying to do high performance, but at the bottom line, they're executing an instruction set which is not all that different from what we're doing today. So is that all there is to building a processor? Well, no, of course you have to do marketing. So we have these little beta inside stickers.